Now, this is a blog post from NeurIPS, and this is announcing the NeurIPS 2025 Best Paper Awards. So this is again kind of an overview of some of these things that I just mentioned. So let's read this article. The Best Paper Award Committee members were nominated by the program chairs and the database and benchmark track chairs, who selected leading researchers across machine learning topics. These nominations were approved by the general chairs and next generation and accessibility chairs. The Best Paper Award committees were tasked with selecting a handful of highly impactful papers from the main track and the datasets and benchmark track of the conference. With that, we are excited to share the news that the Best and Runner-Up Paper Awards this year go to 7 groundbreaking papers, including 4 best papers, one of which is from the datasets and benchmark track, and 3 runners-up. The 7 papers highlight advances in diffusion model theory, self-supervised reinforcement learning, attention mechanisms for large language models, reasoning capabilities in large language models, online learning theory, neural scaling laws, and benchmarking methodologies for language model diversity. So here are the winners. So the first one is artificial hive mind, the open-ended homogeneity of language models and beyond. And this is where we're talking about how all of the outputs of the current frontier models are converging. So the abstract reads, large language models often struggle to generate diverse, human-like creative content, raising concerns about the long-term homogenization of human thought through repeated exposure to similar outputs. Yet scalable methods for evaluating language model output diversity remains limited, especially beyond narrow tasks such as random number or name generation, or beyond repeated sampling from a single model. To address this gap, we introduce Infinity Chat, a large-scale data set of 26,000 diverse, real-world, open-ended user queries that admit a wide range of plausible answers with no single ground truth. We introduce the first comprehensive taxonomy for characterizing the full spectrum of open-ended prompts posted to language models, comprising 6 top-level categories. And so the examples include creative content, generation, brainstorm, and ideation, that further breaks down to 17 subcategories. Using Infinity Chat, we present a large-scale study of mode collapse in language models, revealing a pronounced artificial hive mind effect in open-ended generation of language models, characterized by a few things. The first is intramodal repetition, where a single model consistently generates similar responses. And then more so, number 2, which is intermodal homogeneity, where different models produce strikingly similar outputs. Infinity Chat also includes 31,250 human annotations across absolute ratings and pairwise preferences, with 25 independent human annotations per example. This enables studying collective and individual specific human preferences in response to open-ended queries. Our findings show that state-of-the-art language models, reward models, and language model judges are less well calibrated to human ratings on model generations that elicit differing idiosyncratic annotator preferences, despite maintaining comparable overall quality. So Infinity Chat presents the first large-scale resource for systematically studying real-world open-ended queries to language models, revealing critical insights to guide future research for mitigating long-term AI safety risks posed by the artificial hive mind. So this is just kind of reflections from the selection committee. So this paper made a substantial and timely contribution to the understanding of diversity, pluralism, and societal impact in modern language models. The authors introduced Infinity Chat, which is this model that we talked about. Beyond releasing a valuable data set, this paper provided deep analytical insights through the first comprehensive taxonomy of open-ended prompts and an extensive empirical study across more than 70 models, revealing the artificial hive mind effect, which is pronounced intra and inter-model homogenization that raises serious concerns about long-term risks to human creativity, value plurality, and independent thinking. The findings expose critical miscalibration between current reward models, automated judges, and diverse human preferences, highlighting the tension between alignment and diversity and establishing the foundation for future work on preserving heterogeneity in AI systems. Overall, this work sets a new standard for datasets and benchmarks that advance scientific understanding and address pressing societal changes rather than solely improving technical performance. Okay, so that's the first one. The second paper is Gated Attention for Large Language Models, Nonlinearity, Sparsity, and Attention Sync Free. So this is another paper where they're thinking about these post-transformer architectures, or at least improving the attention mechanism in transformers as they stand today. So the abstract reads, gating mechanisms have been widely utilized from early models like LSTMs and highway networks to recent state space models, linear attention, and also softmax attention. Yet existing literature rarely examines the specific effects of gating. In this work, we conduct comprehensive experiments to systematically investigate gating automated softmax attention variants. Specifically, we perform a comprehensive comparison over 30 variants of 15B mixture of expert models, 15 billion mixture of expert models, and 1.7 billion dense models trained on a 3.5 trillion token dataset. Our central finding is that a simple modification, applying a head-specific sigmoid gate after the scaled dot product attention, or SDPA, consistently improves performance. This modification also enhances training stability, tolerates larger learning rates, and improves scaling properties. By comparing various gating positions and computational variants, we attribute this effectiveness to two key factors. So the first is introducing nonlinearity upon the low-rank mapping of the softmax attention, and the second is applying query-dependent sparse gating scores to modulate the SDPA output. Notably, we find the sparse gating mechanism mitigates massive activation, attention sync, and enhances long context extrapolation performance. We also release related code, which are in these GitHub repositories here, and models which are on Hugging Face here to facilitate future research. Furthermore, the most effective SDPA output gating is used in the QN3 Next models, and these are also hosted on Hugging Face. So this is where they're using this QN3 Next model. They're introducing this gated attention mechanism, and it's available in open source. So the selection committee, what they had to say was that the main finding of this paper is that performance of large language models using the softmax attention can be consistently improved by introducing head-specific sigmoid gating after the scaled dot product, attention operation in both dense and mixture of experts transformer models. This finding is backed up by more than 30 experiments on different variants of gated softmax attention. This paper also includes careful analysis showing that the introduction of the author's recommended form of gating improves the training stability of large language models, reduces the attention sync phenomena that has been widely reported in attention models, and enhances the performance of context-linked extension. The main recommendation of this paper is easily implemented, and given the extensive evidence provided in the paper for this modification to large language model architecture, we expect this idea to be widely adopted. And so this paper represents a substantial amount of work that is possible only with access to industrial scale computing resources and the author's sharing of the results of their work, which will advance the community's understanding of attention in large language models. And so this is a breath of fresh air, apparently, from a lot of the models where the code is proprietary, not open source. So they make a point to talk about how they appreciate this being open sourced. The next paper is 1,000 layer networks for self-supervised reinforcement learning. Scaling depth can enable new goal-reaching capabilities. So this is now moving to reinforcement learning. So the abstract reads, scaling up self-supervised learning has driven breakthroughs in language and vision, yet comparable progress has remained elusive in reinforcement learning. In this paper, we study building blocks for self-supervised reinforcement learning that unlock substantial improvements in scalability, with network depth serving as a critical factor. Whereas most reinforcement learning papers in recent years have relied on shallow architectures of around 2 to 5 layers, we demonstrate that increasing the depth to up to 1,024 layers can significantly boost performance. Our experiments are conducted in an unsupervised goal condition setting where no demonstrations or rewards are provided, so an agent must explore from scratch and learn how to maximize the likelihood of reaching commanded goals. Evaluated on simulated locomotion and manipulation tasks, our approach increases performance on the self-supervised contrastive reinforcement learning algorithm by outperforming other goal condition baselines. Increasing the model depth not only increases success rates, but also qualitatively changes the behaviors learned. So this is reflections from the selection committee again. This paper challenges the conventional assumption that the information provided by reinforcement learning is insufficient to effectively guide the numerous parameters of deep neural networks, hence suggesting that large AI systems be predominantly trained through self-supervision, with reinforcement learning reserved solely for fine-tuning. The work introduces a novel and easy-to-implement reinforcement learning paradigm for the effective training of very deep neural networks, employing self-supervised and contrastive reinforcement learning. The accompanying analysis demonstrates that reinforcement learning can scale efficiently with increasing network depth, leading to the emergence of more sophisticated capabilities. In addition to presenting compelling results, the study includes several useful analyses, for example, for highlighting the important role of batch size scaling for deeper networks within contrastive reinforcement learning. So that is an example of contrastive reinforcement learning and how that is implemented. And then we go to diffusion models. So we're moving from large language models to reinforcement learning to diffusion models. So this one is why diffusion models don't memorize, the role of implicit dynamical regularization in training. And so this abstract reads, diffusion models have achieved remarkable success across a wide range of generative tasks. A key challenge is understanding the mechanisms that prevent the memorization of training data and allow generalization. In this work, we investigate the role of the training dynamics in the transition from generalization to memorization. Through extensive experiments and theoretical analysis, we identify 2 distinct timescales. The first is an early time at which models begin to generate high-quality samples, and the second is a later time beyond which memorization emerges. So we have these 2 different timescales that the model operates on. So it's this generative part that's early, and then this memorization at a later time. Crucially, we find that increases linearly with the training set size while remaining constant. This creates a growing window of training times where models generalize effectively, despite showing strong memorization if training continues beyond it. It is only when it becomes larger than a model-dependent threshold that overfitting disappears at infinite training times. These findings reveal that a form of implicit dynamical regularization in the training dynamics, which allows to avoid memorization even in highly overparameterized settings. Our results are supported by numerical experiments with standard UNet architectures on realistic and synthetic datasets, and by a theoretical analysis using a tractable random features model studied in a high-dimensional limit. So the selection committee said, this paper presents foundational work on the implicit regularization dynamics of diffusion models, delivering a powerful result by unifying empirical observation with formal theory. The critical finding is that quantitative identification of 2 distinct predictable timescales, an early dataset independent generalization phase, followed by a linear dataset size dependent memorization phase. So it's dataset independent versus dataset dependent. This demonstration of an expanding window for effective generalization is not merely an empirical finding, but is rigorously explained by deriving the spectral properties of the random features model using random matrix theory. By linking the practical success of diffusion models directly to a provable dynamical property, the implicit postponement of overfitting, this paper provides fundamental, actionable insight into the mechanisms governing modern generative AI, setting a new standard for analytical depth in the study of generalization. Okay, so those are the winners of this, it's the best paper award. Because it's a big conference, you have to have 4 of them. So there are a bunch of runners-up as well. So the first one is, does reinforcement learning really incentivize reasoning capacity in large language models beyond the base model? And so they're doing this method called reinforcement learning with verifiable rewards, or RLVR. Has recently demonstrated notable success in enhancing reasoning performance of large language models, particularly mathematics and programming tasks. It is widely believed that, similar to how traditional reinforcement learning helps agents to explore and learn new strategies, RLVR enables large language models to continuously self-improve, thus acquiring novel reasoning abilities that exceed the capacity of the corresponding base models. In this study, we take a critical look at the current state of RLVR by systematically probing the reasoning capability boundaries of RLVR-trained large language models across diverse model families, reinforcement learning algorithms, and math/coding/visual reasoning benchmarks, using at-large values as the evaluation metric. With RLVR improved sampling efficiency towards the correct path, we surprisingly find that the current training does not elicit fundamentally new reasoning patterns. We observe that while RLVR-trained models outperform their base models at smaller values, base models achieve higher scores when it is large. Moreover, we observe that reasoning capability boundary of large language models often narrows as RLVR training progresses. Further coverage and perplexity analysis shows that the reasoning paths generated by RLVR models are already included in the base model sampling distribution, suggesting that their reasoning abilities originate from and are bounded by the base model. From this perspective, treating the base model as an upper bound, our quantitative analysis shows that 6 popular RLVR algorithms perform similarly and remain far from optimal and fully leveraging the potential of the base model. In contrast, we find that distillation can introduce new reasoning patterns from the teacher and genuinely expand the model's reasoning capabilities. Taken together, our findings suggest that the current RLVR methods do not fully realize the potential of reinforcement learning to elicit genuinely novel reasoning abilities in large language models. This underscores the need for improved reinforcement learning paradigms, such as continual scaling and multi-turn agent environment interaction, to unlock this potential. So RLVR sounds like an interesting area, and they're kind of tying in other types of agentive learning into this. So the selection committee says this paper delivers a masterfully executed and critically important negative finding on a widely accepted foundational assumption in large language model research, that reinforcement learning with verifiable rewards elicits genuinely new reasoning capabilities. The paper shows that RLVR training across various model families, tasks, and algorithms enhances sampling efficiency without expanding reasoning capacity already present in base models. Reinforcement learning narrows exploration, rewarded trajectories are amplified, but the broader solution space shrinks, revealing that RLVR optimizes within rather than beyond the base distribution. This is an important finding which will hopefully incentivize fundamentally new reinforcement learning paradigms, able to navigate the vast action space and genuinely expand large language model reasoning capabilities. So that's interesting that they kind of have they work out these sort of dynamics for reinforcement learning um, with application of large language models. Okay. This next one is optimal mistake bounds for transductive online learning. So this abstract says we resolve a 30-year-old open problem concerning the power of unlabeled data in online learning by tightly quantifying the gap between transductive and standard online learning. We prove that for every concept class with little stone dimension, the transductive mistake bound is at least, and they don't have there are some formatting problems with this blog post. This establishes an exponential improvement over previous lower bounds of, and respectively due to this citation here and this other citation. So the first is Ben David, Kushelowitz and Mansour, 1995-1997, and Henneke, Moran, and Schaefer, 2023. We also show that our bound is tight. For every, it's supposed to be a symbol there exists a class of little stone dimension with transductive mistake bound. Our upper bound also improves the previous best known upper bound from Ben David. These results demonstrate a quadratic gap between the transductive and standard online learning, thereby highlighting the benefit of advanced access to the unlabeled instance sequence. This stands in stark contrast to the PAC setting, where transductive and standard learning exhibit simple sample complexities. So this is, so the selection committee says, this paper presents a breakthrough in learning theory, deserving the NeurIPS Best Paper Runner-Up Award for its elegant, comprehensive, and definitive resolution of a 30-year-old open problem. The authors not only precisely quantified the optimal mistake bound for transductive online learning, but they've also achieved a tight match with an upper bound. This establishes a quadratic gap between transductive and standard online learning, a result that represents an exponential leap beyond all previous logarithmic lower bounds, and dramatically highlights the theoretical value of unlabeled data in this setting, a crucial insight distinct from its more limited role in PAC learning. So what does this mean? I'm not really sure. This is largely a proof, so it's an open problem in the field. I'm not really familiar with this problem. This is really just thinking about how you can do online learning without labels, and it's just an example of how this is kind of worked out mathematically. So some of the insights here. For the lower bound, the adversary employs a sophisticated strategy that balances forcing mistakes with carefully managing the shrinking of the version space, leveraging the concept of paths and trees as a fundamental underlying structure. The upper bound, demonstrating the learnability within these mistakes, introduces an innovative hypothesis class construction that embeds a sparse coding for off-path nodes, a probabilistic design where most off-path labels are zero, but the rare ones carry immense information. The learner's strategy to exploit this class is equally brilliant, integrating several non-standard sophisticated techniques, for example, danger zone minimization to control the instance sequence presented by the adversary, splitting experts via multiplicative weights approach to handle uncertainty about a node's on-path status, and a strategic transition to halving when sufficient information is gathered from the sparsely encoded off-path labels. This intricate interplay between a cleverly constructed hypothesis class and a highly adaptive learning algorithm showcases a masterclass in theoretical analysis and design. So that's a good paper there. This next paper, Superposition Yields Robust Neural Scaling. This is the success of today's large language models depends on the observation that larger models perform better. However, the origin of this neural scaling law, that loss decreases as a power law with model size, remains unclear. We propose that representation superposition, meaning that large language models represent more features than they have dimensions, can be a key contributor to loss and cause neural scaling. Based on Anthropic's toy model, we used weight decay to control the degree of superposition, allowing us to systematically study how loss scales with model size. When superposition is weak, the loss follows a power law only if data feature frequencies are power law distributed. In contrast, under strong superposition, the loss generically scales inversely with model dimension across a broad class of frequency distributions due to geometric overlaps between representation vectors. We confirm that open source large language models operate in the strong superposition regime and have loss scaling inversely with model dimension, and that chinchilla scaling laws are also consistent with this behavior. Our results identify representation superposition as a central driver of neural scaling laws, providing insights into questions like when neural scaling laws can be improved and when they will break down. And so the selection committee says, this paper moves beyond observations of neural scaling laws. The empirically established phenomena in which model loss exhibits a power law decrease as model size, dataset size, or computational resources are increased, to demonstrate that representation superposition constitutes the primary mechanism governing these laws. Authors introduce a controlled toy model to examine how superposition and data structure affect the scaling of loss with model size and demonstrate that under strong superposition, where features are overlapping, the loss scales consistently as an inverse power law with respect to the model dimension. The core findings are supported by a series of carefully designed experiments and offer fresh insights into an important research area. So these are their papers that they've given awards to for this year, and that is all we have there. Okay, the other thing that we should probably go over is the 2025 Sejnowski-Hinton Prize. So the NeurIPS Organizing Committee is pleased to announce the winner of the 2025 Sejnowski-Hinton Prize, and this is Tim Lillicrap, Daniel Condon, Douglas Tweed, and Colin Ackerman for their groundbreaking 2016 paper, Random Synaptic Feedback Weights Support Error Backpropagation for Deep Learning. This was published in Nature Communications as is also available on the archive. So this is, I guess, a paper, like the best paper of all time that they kind of pick and kind of bring it back into relevance today. So this is, the topic of this paper is feedback alignment. And we'll talk about that paper later, but I wanted to kind of go over this blog post and see what they have to say about it. So theories of the brain have long sought to explain how neural circuits learn efficiently using only local information. And so this is, an example. This is how synapses adjust based on signals available at each connection, rather than through some explicit global error propagation. So you're correcting things locally, you're processing information locally, and this happens at every synapse. You can assume some sort of global error propagation, but that's not really the way the network works. Inspired by this challenge, researchers have explored ways to train artificial neural networks that perform gradient descent using local learning rules. This paper is recognized for its contribution to that pursuit through the discovery of feedback alignment. The authors demonstrated that multi-layer networks can learn effectively when fixed, using fixed random feedback weights, rather than requiring exact backwards weight symmetry as in backpropagation. So you have these sort of random feedback weights that come from the local interactions of the synapses. Remarkably, the network's forwarded weights naturally align with these random feedback signals over the course of learning, yielding a biased yet useful estimate of the loss gradient. This insight provided the first concrete biologically grounded solution to the long-standing weight transport problem, the question of how real neurons follow loss gradients without non-local information transfer. And so this work had significant impact, helping to establish a new subfield of biologically plausible learning rules in the NeurIPS community and beyond. So basically, the Sejnowski-Hinton Prize is awarded annually to a paper published within the past 10 years that has made major contributions to computational theories of the brain, especially drawing insights from artificial intelligence, and has had a significant impact on the NeurIPS community.